Good morning. Hello. Hi. 안녕하세요. 여러분. Hi. How are you doing, everyone? This is the final stretch of the semester and of this course. So we're currently talking about computational complexity theory. This is a recap of the theory of NP completeness that maybe some of you are already familiar with. This course is about algorithm design and analysis, not about complexity theory. There's a separate course that treats computability and complexity theory in depth. That's CS422. So in the present course, we only briefly recall some basic notions and properties that are relevant in order to appreciate the next and more central chapter that will be chapter 8 on approximation algorithms. So the motivation for considering approximation algorithms is, as we're going to see in this chapter 7, complexity theory, that some optimization problems probably cannot be solved in polynomial time unless the millennium problem P versus NP has a surprising answer. So this is what we're doing right now, and we're kind of approaching the end of the lecture. So maybe chapter 8 on approximation algorithms will actually be the last chapter. And of course, there will be a final short chapter, a conclusion, and recap. So that's our plan for now. So let me resume the lecture slides. So we are talking about chapter 7 on computational complexity theory. And in this chapter, we will recall the complexity classes P and NP of decision problems. We talk about certain decision problems on graphs, Eulerian cycle problem, Hamiltonian cycle problem. Another pair of decision problems on graphs is the edge cover versus the vertex cover problem. And we talk another pair of problems over graphs, Clique problem and independent set problem. And we will then recall and learn a way of how to compare the complexity, the inherent cost of decision problems, whose complexity we don't know. That's, in a sense, this is a really a highlight of the scientific method. I will tell more about that when we talk about this slide. And finally, we will discuss two optimization problems that are NP hard, the traveling salesperson problem and the knapsack problem, because these will be among the problems that for which we will then in chapter 8 design and analyze approximation algorithms. So complexity class P and NP. So here we're talking about decision problems, and we formalize a decision problem as a set of finite binary strings, usually an infinite set, but every element of that set is a finite binary string. And we say that such a decision problem is decidable in polynomial time if there exists an algorithm which, when presented with some finite binary string, let's say a binary string of length n, then the algorithm within finite time answers whether this string belongs to L or does not belong to L. So let's see, there's a right. So, and the class P, the famous class P, is the class of all decision problems that can be solved in polynomial time in this very sense. Whereas the class NP, exp is a class of all decision problems that can be solved, that can be answered in exponential time, in time exponential in the length. The binary length is our prime measure of our complexity parameter. And of course, polynomial time is a special case of exponential time. Polynomial time includes, for instance, n to the 6. That's the running time of the current best deterministic algorithm for testing whether a given integer is a prime number, the AKS primality test. And exponential time also includes such running times like 2 to the n squared, 2 to the n to the 6, but not 2 to the 2 to the n. That's double exponential. That's the Ackermann hierarchy that we talked about when we discussed slow and fast growing functions. And between these two classes, for which complexity theory has achieved to show that they're different, they're classes for which we don't know whether they're different, or more precisely, whether they're different from P or from X, or different from both. And that's this famous complexity class P, the class of all decision problems we can be verified in polynomial time. Now, what does it mean to be verifiable in polynomial time? In the sense that's a kind of artificial definition, but the reason for that definition is that because there are many problems that can easily be shown to belong to this class NP, but for which we don't know whether they belong to the purportedly smaller class P. So what does it mean to be polynomial time verifiable? It means that the set of finite binary strings is of the following syntactical form. So this is a syntactical definition of NP. And just for reference, there's also a semantical definition, a definition that is based on non-deterministic polynomial time Turing machines. But in this brief recap, we're going to avoid talking about Turing machines. So what is a syntactical definition of NP? It's a set of all finite binary strings X with a property that there exists a Y, and Y will be called a witness of length, which is bounded polynomially in the length of X. So it could be, for instance, at most the length of X, but it could also be at most the quadratic length of X, or to the 6th power, with the following property that the pair X comma Y belongs to this other decision problem V, which is in turn polynomial time decidable. So to define NP, we need kind of two parameters. One is the parameter, the verifier, the decision problem V, and the other is the polynomial bound. And different polynomial time bounds and different verifiers give rise to these different decision problems that are, by the very definition, all in NP. NP comprises all decision problems of this form. And since this is a very abstract definition, we're going to consider many examples in the following slides. So don't worry if this is all alien to you. So here's the first example. This is the set of all complements of binary encodings of prime numbers. Let me say that again. So what you see here on the right, these are binary encodings of prime numbers. This is a binary encoding of 2, binary encoding of 3, binary encoding of 5, 7, that's 11, that's 13, and so on. And here we have this backslash, the set minus sign, which means that L consists of all binary strings which are not binary encodings of prime number. So deciding L as a decision problem thus formalizes the question whether a given integer is not a prime number. It belongs to L if and only if its binary encoding, integer is not a prime number if and only if its binary code does not belong, its we say number is not a prime number if and only if its binary code does belong to L. Right. So, and we have seen algorithms, randomized algorithms that tell that with one-sided error, Monte Carlo algorithms. But here we're going to look at the not randomized algorithm. There's no probability distribution we're talking about, but only the question of whether there exists a witness. And to show that this decision problem, the set of all binary strings which are not binary encodings of prime numbers, that this belongs to NP. Our job is to reformulate the set L in this syntactical form. So that's why I call it a syntactical definition of NP. So, and this is a nice kind of exercise because there may be similar problems in the homework and or final exam. So how do we rewrite L? So it should be the same set L, but rewritten in this syntactical form. And here's one possible answer. Namely, we say we consider particular polynomial, namely the identity polynomial, and we consider particular decision problem V, namely the decision problem given two binary strings x and y. Is it true that the binary encoding of y is greater than 1 and divides the binary encoding of x? So this is a decision problem given codes of x and y. Check whether the binary encoding of y is strictly greater than 1 and check whether the binary encoding of y divides x. And these are both tests that can easily be performed. Yeah, so comparing this is straightforward, right, from the binary code. And this is just your favorite division with remainder algorithm, which takes a number of steps that is polynomial in the binary length. And that's precisely our definition, right, of polynomial time always means polynomial in the binary length. And right, so standard long division of binary numbers achieves that, so that this part can be actually replaced by the condition that the pair x comma y belongs to V, where V is just the set of x comma y that satisfy this property, standard polynomial time decidable decision problem. And what about the first condition? Binary length of y is strictly less than x. That basically means that y must be a proper divisor, whereas this means that y must be a divisor and a non-trivial divisor. So that this is indeed a reformulation. This is the same set as L. It's a set of all binary strings which are not a prime number, all binary strings for which there exists a proper divisor. This proper divisor is what we call y here in binary encoding. And in the terminology of NP, this is thus a witness, binary encoding of a proper divisor that serves as witness in this example for reformulating the decision problem L in the form NP. And observe where we had to do some creative tasks, namely we had to find kind of some meaning, some semantics of what we consider and choose as a witness. So to conclude, we have succeeded reformulating these decision problems as an NP problem, as a problem of the syntactic form. But of course, right, and since we have this hierarchy, right, P is included in NP, NP is included in exponential time. Therefore, this decision problem is also decidable in exponential time. But we knew that, right? So the sieve of Eratosthenes, for instance, is already an exponential time algorithm. So the question that used to be open for a long time until 2003 was whether there exists a polynomial time algorithm. until 2003, we knew that there's randomized algorithms, Miller-Rabin, for instance. We knew that the problem belongs to NP, as seen here, but whether it belongs to NP, that was also only answered, resolved in 2003. Good, so that was our first example, and in the sequel I will keep this syntactical definition of NP on the bottom of the slide for your convenience and reference. So let's now consider more example problems in NP, namely both the Eulerian cycle and the Hamiltonian cycle problem. So what is Eulerian cycle? What is Hamiltonian cycle? For Eulerian cycle, we're going to consider a graph, an undirected graph, which may or may not be a multi-graph. And understand that you're all familiar with graph, with this concept and terminology from attending CS204 discrete mathematics. And to motivate the Eulerian cycle problem, the following question about the Prussian city of Königsberg was posed to Leonhard Euler. Is it possible to start at some place in Königsberg, let's say here, and then cross every bridge precisely once, and then return to the original position? So let me say it again. Start somewhere, then walk around and return to the original position. That's why it's called a cycle. And cross every bridge precisely once, not twice, and not miss any bridge, just return. That's the Eulerian cycle problem for the city of Königsberg. And the first thing that Euler did was to make this problem more abstract and more general. He was a mathematician, after all, a famous mathematician, right? So 2 steps: make the problem abstract and make the problem more general, refer not just to the case of Königsberg, but other cities, or even more general. So to this end, he replaced the bridges with the edges of a graph. So in this case, Königsberg had 7 bridges, and so this gave rise to 7 edges, undirected edges, because every bridge can be crossed in either direction. And these edges, these bridges, connect between vertices, between locations that can be traversed without having to cross over a bridge. And there are 4 of these locations in Königsberg. So the Eulerian cycle problem is the following: given as input a graph, undirected multigraph, and here we already have a multigraph, because for instance between these 2 vertices there are 2 different edges connecting the same pair of vertices. And the question is there a cycle that traverses every edge precisely once? So that's the generalization and abstraction performed by Euler. Namely, he got rid of the underlying map entirely and only talks about a decision problem concerning graphs. So in our formulation, where a decision problem is a subset of binary strings, we encode such a graph, multigraph, as a finite binary string. There are many ways for doing that. For instance, one could encode the adjacency matrix of the vertices. So if there are n vertices, then the adjacency matrix is an n times n matrix. And the entries in the matrix tell us whether there is and actually how many edges there are between the vertex that occur in the number and in the column of the entry of the matrix. And then just enumerate all the entries in the matrix in binary. That's one way of encoding a graph as a finite binary string. And our decision problem is the problem of all such encodings of graphs which do have a Eulerian cycle. Put differently, given a graph, given an encoding of such a graph, belongs to the set or not means, does it have a Eulerian cycle or not? So that's our decision problem. And the first observation is that this is a problem in NP. So let's again practice showing that a certain problem is in our syntactical definition of NP. And we practice that by kind of conceiving a witness. So what could possibly be a witness for a graph to have a Eulerian cycle? Well, the Eulerian cycle itself, because verifying whether a given Eulerian cycle is indeed a Eulerian cycle, that should be easy, that should be feasible in polynomial time. That's our verifier, right? So how do we formalize a Eulerian cycle as a finite binary string? For instance, we could do that by listing the vertices, the numbers of the vertices occurring in the cycle in the very order that they occur in the cycle. So if we have a graph of n vertices, then specifying the number of the one vertex that takes log n bits roughly, right? So the number of a vertex, if there are n vertices, then the numbers range from 1 to n, and therefore the length of the binary codes of these numbers range up to log n. And so Eulerian cycle is a list of such binary encoded vertices of log n bits each, and the cycle must visit every vertex once. So the cycle has length n. So that means a total of n log n bits could be used to encode the Eulerian cycle, and that in turn will be a witness to a graph having Eulerian cycle. And observe that n log n is indeed polynomial, right? It's n log n. That's a very small polynomial. And given such a encoding of a Eulerian cycle, we just need to verify whether it is a Eulerian cycle by following the sequence of binary encoded vertex numbers. And for each successor, check whether there is indeed an edge in the graph connecting the previous to the current vertex. Otherwise, this is not a cycle, right? The cycle may only follow edges that are present in the graph. And finally, check whether in this cycle really every vertex occurs precisely once. That's also easy to check. So to summarize, we have just rephrased the Eulerian cycle problem in the form of an NP problem where now the witness y, we conceive the witness y, we give the semantics to the witness y to be the binary encoding of a purported Eulerian cycle. Binary encoding, we've verified this has polynomial length, and whether it is actually a Eulerian cycle, this is something that can be decided in polynomial time. So that's so much about the Eulerian cycle problem. And now we're going to similarly discuss the Hamiltonian cycle problem. So what is a Hamiltonian cycle? It's also a cycle, so it's also a tour in a graph starting at some vertex and returning to that very same vertex. And here the condition, the requirement is that the Hamiltonian cycle must visit every vertex precisely once. So it must not miss any vertex. It must not miss any vertex twice, but it can miss some edges. So this is a perhaps subtle but important distinction between Eulerian cycle and Hamiltonian cycle. Eulerian cycle must visit every edge precisely once, but it can visit some vertices twice or even 3 times if it wishes to, right? A Hamiltonian cycle, on the other hand, must visit every vertex precisely once, but it is allowed to miss some edges if it prefers to. So here's an example. Oh, there's the images are including. No, it's okay. It's visible, right? So here you see a graph with how many? 5, 10, 15, is that 15 vertex? No, it's 20 vertices, right? It's 20 vertices, and my claim is that this graph has a Hamiltonian cycle. So how can I convince you that this graph has a Hamiltonian cycle? Well, by presenting a witness. And remember, the nice thing about NP problems, it's easy to convince someone that the string X belongs to the set L, maybe by presenting a witness. Why? Because then it is easy for your partner to verify that this is indeed a witness. Easy in the sense that verifying whether it is a witness or not is polynomial time decidable. So let's do that here kind of in practice to convince you that this graph with 20 vertices has a Euler Hamiltonian cycle. I'm just going to present to you Hamiltonian cycle, and here it is, right? So as you can see, the red edges form a cycle. Start anywhere, you're going to return to the very same vertex, and this tour will visit every vertex precisely once. So this is kind of a witness of this graph having a Hamiltonian cycle. And on a more formal perspective, this witness has polynomial length, namely it's in this case now it's a sequence of edges that form the cycle, right? So when we talked about a witness for a graph to have a Eulerian cycle, we would talk about the sequence of vertices, start somewhere, return to the same vertex, and on the in between visit every edge precisely once. Here to convince you that this is indeed a Hamiltonian cycle, similarly encode the sequence of edges, and every edge has roughly, in the worst case, n squared times log n as log n bits again. And since every edge is visited precisely once, there's a total number m of edges, and m is at most quadratic, m is at most n squared, so that the length of a witness here, the sequence of edges traversed by the Hamiltonian cycle, is indeed at most polynomial. And again, it's easy to verify that this is a witness simply by following the sequence of edges and verifying that every edge is indeed present in the original graph, and checking off the vertices visited as part of this tour to make sure that precisely every vertex is visited precisely once. So to summarize, also the Hamiltonian cycle problem. Here's another example. So this graph, let's look at this graph, and I claim that this graph does not have a Hamiltonian cycle. How can I convince you that this graph does not have a Hamiltonian cycle? This is a more delicate issue, right? Because in order to really formally verify, to prove rigorously that this graph does not have a Hamiltonian cycle, we would need to consider all possible candidate cycles and then check that every single one of them is not Hamiltonian. Every single one violates at least one of the conditions. Either it doesn't return to the original vertex, or it misses some vertex, or it visits some vertex twice, right? And this is tedious. So it seems that um, showing that this graph does not have Hamiltonian cycle is difficult, or put differently, more formally, um, showing that some finite binary string does not belong to the set of encodings of Hamiltonian cycles. That's more difficult than to show that a certain encoding of a graph has a Hamiltonian cycle. So to move on, so this is a formalization of the Hamiltonian cycle problem. It basically looks the same as a Eulerian cycle problem, EC and HC, and we've seen that both belong to NP. We've reformulated both of them as in the syntactic form, as where X here belongs represents the binary encoding of the graph, and Y in the first case represents candidate Eulerian cycle, a sequence of edges, whereas it represents a candidate Hamiltonian cycle, a sequence of vertices. In the second case, in both cases, the length of this witness is indeed polynomial in the length of X, and verifying that it is a witness can be done in polynomial time, so that here we have two natural problems on top of the problem with a given natural number is not a prime number, two natural examples about graph problems that belong to NP. Now, the maybe funny thing is that there's a subtle difference between the two problems, subtle difference that gives rise to huge difference in computational complexity, namely the Eulerian cycle problem actually can be solved in polynomial time. So while it is true, as we said, that it belongs to NP in our hierarchy, we can actually also locate it somewhere closer, namely in the smaller complexity class P. Remind you of the syntactic definition of NP. The class NP consists of all decision problems that have the following syntactic form. The form is the following. A decision problem L belongs to this class NP if and only if it has this syntactic form. And so in order to prove that a decision problem belongs to NP, we need to rephrase the problem in this syntactic form. And the syntactic form is the following. The problem has this form if it consists of all this finite binary strings X, to which there exists a finite binary string Y. We call this Y the witness. The witness must have length at most polynomial in the length of X. And the property of being a witness, or put differently, given a pair X, the input, and Y, the candidate witness, whether it is a witness or not, must be decidable in polynomial time. So this is this. And thank you. We've discussed, we've reformulated the Eulerian cycle problem in this form. So when we reformulate Eulerian cycle problem in this form, X amounts to this encoding of a graph, right? That's our finite binary string X is the encoding of the graph. These angle brackets are to indicate that we're talking about encoding of a graph as a finite binary string. And as a witness for this graph to have a Eulerian cycle, we consider the very Eulerian cycle. We consider the sequence of edges in the very order that they are traversed as part of this Eulerian cycle. And we've verified that this our conception of this witness, the length of Y in binary, the binary encoding of the sequence of vertices is visited as part of this Eulerian cycle, has length n log n, which is certainly polynomial in n the binary length of the input, so that this property is satisfied by our conception of Y as a witness to the graph having a Eulerian cycle. And then we verify that the property that the Y is a Eulerian cycle in this graph G, in this graph encoded by X, that this property can be verified in polynomial time simply by following the sequence of edges, which is polynomial time algorithm. And similarly, we have reformulated your Hamiltonian cycle problem in this syntactic form. Again, here X corresponds to the binary encoding of a given graph G. And to check whether this graph has a Hamiltonian cycle, a witness that helps us verifying that is the Hamiltonian cycle itself, is the sequence of vertices in the very order in which they are visited. Again, this binary encoding of a sequence of vertices of at most n vertices has a total length of at most n log n, and verifying that this sequence indeed constitutes the Hamiltonian cycle, that the pair x comma y, the pair graph comma Eulerian Hamiltonian cycle, that this is indeed a Eulerian cycle, a Hamiltonian cycle of the graph. This can be decided easily in polynomial time. Thank you. Yes. So in this formalization, we talk about finite binary strings, right? So X is a finite binary string, Y is a finite binary string, and every finite binary string has some length, right? So for instance, the binary string 1101, this is a string of length 4. And that's the length, and we use this vertical bars to indicate the length of the string. So the graph is encoded as a finite binary string using, and these angle brackets are used to indicate that. And we, when we have the task of expressing such a decision problem about finite binary strings as an NP problem, we must come up with a semantical conception of what should be a witness. The witness must be a finite binary string. So in doing so, in this example, we conceive this finite binary string witness Y to be the binary encoding of a Hamiltonian or Eulerian cycle. Yes, this is indeed, this is all rather abstract stuff. This is, in the sense, the pinnacle of computational complexity theory. This is what the Millennium Problem is about. So if someone can answer the P versus NP question, to which we will say a little bit more later, it will be rewarded with $1 million, right? So indeed, you're right. This is pretty abstract and advanced topic in computational complexity theory, and I'm happy to explain that, to convey it as far as possible. But for the purpose of this current lecture, it suffices that we only recap the basics. So we're currently talking about the Eulerian cycle problem, which we have just argued to belong to this class NP, same as a Hamiltonian cycle problem, but actually the Eulerian cycle problem also belongs to this smaller class P. It can be decided, not just verified, but decided in polynomial time, in time polynomial, in the size of the binary encoding of the graph, which is polynomial in the number of vertices and also polynomial in the number of edges. And this polynomial time algorithm for the Eulerian cycle problem is based on the following purely mathematical statement inside, namely, if a graph has no isolated vertices, then this graph admits a Eulerian cycle if and only if it satisfies the following two properties. The graph is A, it is connected, and B, every vertex of the graph has even degree. So I'm not going to prove this statement here. That's just a standard exercise, maybe in discrete math or maybe in graph theory as offered by the math department. But the thing is, we can use that statement of the lemma to immediately come up with a polynomial time algorithm for the Eulerian cycle problem. Namely, we just need to verify the two properties, that the graph is connected, and you all know, for instance, Dijkstra's algorithm can do that, and to verify that every vertex in this graph has even degree, that's also very easy to check, right? So for rephrasing, that's the achievement of the lemma. Rephrasing what superficially could seem like a hard problem, could seem like an NP problem, could seem to require testing all possible cycles, of which there are n factorial many, exponentially many. But the lemma allows us to rephrase this property in terms of something that can be checked very easily, namely that the graph is connected and every vertex in the graph has even degree. And the hypothesis of the lemma that the graph has no isolated vertices comes basically for free, because we can just remove all isolated vertices. The presence or absence of isolated vertices does not change whether the graph has a Eulerian cycle or not. So that based on this lemma, one easily can devise, I will refrain from actually doing so in detail, but we can easily come up with a polynomial time algorithm. So meaning that our original assessment that the Eulerian cycle problem belongs to NP is still true, but it's kind of not optimal. We have been able to devise a polynomial time algorithm, and yeah, that's as good as we can get polynomial time algorithm, right? Good, so that's our first two examples of problems on graphs that look very similar. But for one problem, we have been able to devise an optimal algorithm. Polynomial time is optimal, right? For the other problem, we've only been able to show that it belongs to NP, but we don't know whether it belongs to P or not, whether it admits a more efficient deterministic solution. So that's these two problems. Now we're moving on to two other decision problems on graphs. Maybe the edge cover and the vertex cover problem. So edge cover is the following problem. Given a graph, what is the size of a smallest edge cover? What is an edge cover? An edge cover is a subset of the edges, such that every vertex in the graph is endpoint to at least one of the edges. So here you see a graph with 6 vertices and 7 edges, right? And this graph has a vertex cover of size 3, namely the 3 edges painted in red. They, in a sense, cover the vertices, namely every vertex is an endpoint to at least one of the red edges, so that the 3 red edges form an edge cover of this graph of size 3. And this is a minimum edge cover. There is no way to cover all vertices with only 2 edges, with less than 3 edges. So this is a edge cover. And now let's look at the graph on the right. This graph on the right also has 6 vertices and 6 edges. And here this minimum edge cover is consists of 4 edges. So again, here you see 4 edges are marked. 2 are marked red and 2 are marked blue. And these 4 edges together have also the property that every vertex is endpoint to at least one of these edges. So that here in the graph to the right, we have an edge cover of size 4. And again, this is a minimum edge cover. There is no edge cover of size 3. No 3 edges can have this property that every vertex is an endpoint to one of the 3 edges. I leave this to you to convince yourself that this is indeed true. So the minimum edge cover problem is a problem given a graph. What is the size of a smallest edge cover? Now, if you listen carefully, what I'm stating here is not a decision problem. I'm asking what is the size of a smallest edge cover. That's the answer is not yes, no, as required for a decision problem, but the answer is an integer, a number, a size of an edge cover. So this does not fit into our framework here, right? In our framework, we only talk about decision problems, but this is not a decision problem. So in order to bring this problem into our framework, we make a following trick, which is a standard. We will apply this several times again in the course of this chapter 7. And we reformulate this function problem asking for the size, that's an integer valued function, as a decision problem, namely given a graph and given an integer k, does there exist an edge cover of size at most k? Size at most k, or that's the same, that's equivalent, an edge cover of size k. Now this is a decision problem. The answer to this problem is either yes or no. Either there exists an edge cover of size k, or there is no edge cover of size k. That's a yes/no problem. And this is in a sense that I will not formalize further. In a sense, this decision problem is equivalent to the function problem, to the minimization problem that we're originally interested in. So what you see here in the second line on the bottom of this slide in yellow, this is the mathematical, the logical formalization of the edge cover problem as a decision problem, given the binary encoding. Remember, these angle brackets indicate binary encoding, so that we're talking about finite binary strings as in order to fit into our setting. Given the binary encoding of a set of vertices, of a set of edges, and of a natural number k, is it true that there exists a subset of the edges, which we're going to call f, of size k? So here the vertical bars mean the cardinality of the set, with a property that every vertex is endpoint to some edge in this subset f. So here the subset f is comprised of all red edges in this example, and in this example the subset f is comprised of all red or blue edges, and the total set of edges E here is all edges regardless of their color, or here also all edges regardless of their color. Right. And the other decision problem we want to consider in this slide is the vertex cover problem, which again seems very similar. So for the vertex cover problem, again given a graph, and this time we want to find what is the minimum size vertex cover, the smallest subset, such that every edge has at least one of the vertices as endpoint. So this is the vertex cover decision problem. Find a small subset of vertices such that every possible edge in the graph has at least one of these vertices among its two endpoints. So, first observation is that by the very formulation on the bottom of the slide of EC, this is a NP problem. This is a problem of the syntactic form NP. This is a problem with witnesses of polynomial length and polynomial time decidable, all polynomial in the binary length of the original graph of the original input. Let's check that more closely. So what is our conception? What is our assignment for witness? What could be a witness for graph to have a small edge cover? Well, the subset of edges themselves, right? So if you just look syntactically, this is kind of our x, right? Binary encoding of something. This is a binary string, this is x. Then there's this existential quantifier, something exists, here something exists. So we only need to bring this, which is a subset of the edges, into the form finite binary string. How do we encode the subset of the edges as a finite binary string For instance, we could encode the subset of the edges as a characteristic function. For every edge in capital E, bit 0 is used to indicate that this edge does not belong to F, and bit 1 indicates that this edge belongs to F, so that in the end we can encode this subset of the edges as a finite binary string of length m, where m denotes the number of edges. So let's continue. Let's pursue this conception of a possible witness, a binary string that has bit 1 at position corresponding to edges that belong to F, and has bit 0 at positions that do not belong to F. Then the requirement is that this set has cardinality k, so that means that in our binary string, the number of bits 1 occurring must be precisely k. Again, that's something that can be verified very easily. And the final condition also is polynomial time verifiable. When we look at every vertex x, look for some adjacent vertex, right? Y. This means that the vertex is adjacent, and that the edge from x to y is in our subset, that the corresponding position in our string y encoding the set of subset f by its characteristic function. The corresponding position is a 1, meaning that it is present. So then this is a witness of polynomial length. It's actually same length as the set E of edges, and verifying that this is edge cover is easy in the sense that it can be done in polynomial time. I'll leave it to you to actually design and analyze this verification algorithm. That's easy. So to summarize, the edge cover problem is in NP, but while this is true, this is not optimal. It's not optimal as for the similar reason as the Eulerian cycle on the previous slide was in NP, but actually this was not optimal. It was even in P. We have been able to find a polynomial time algorithm for the Eulerian cycle problem, and similarly we can find a polynomial time algorithm for the edge cover decision problem. And what is this polynomial time algorithm? We take a maximum matching, we compute a maximum matching, and remember from our last chapter that Jack Edmonds' Blossom algorithm achieves exactly that. So the Jack Edmonds Blossom algorithm, which we did not discuss in detail but mention, can find a maximum matching in a given graph. So let's use that algorithm as a subroutine and then extend that maximum matching in order to cover every single vertex, right? So again, looking from this perspective of these examples, here the Jack Edmonds algorithm might come up with a maximum matching, namely the 3 red edges, and then there's no need to further extend because the 3 red edges already form an edge cover. In the other example in this graph, here the Edmonds algorithm might come up with a maximum matching consisting of the 2 red edges, and then we greedily extend Edmonds matching provided by Edmonds algorithm, such as to cover also the remaining vertices. In this case, the remaining vertices are the one that are covered by these 2 blue edges. And Edmonds' algorithm is a polynomial time algorithm, and greedily extending is also polynomial time, so that in total, this is a polynomial time algorithm for the edge cover problem, and the edge cover, therefore, is a polynomial time decidable problem. So it's still true that it belongs to P in the hierarchy, but actually it belongs to this smaller class in the hierarchy to P. For the vertex cover problem, we don't know. For the vertex cover problem, we know for a similar reason that we can we can see for similar reasons that it belongs to NP. So on the bottom of the slide, now you see the formalization of the edge cover problem replaced by the formalization of the vertex cover problem. So again, we're looking for minimum vertex cover, but we rephrase this optimization, minimization problem as a decision problem, given a graph and given a natural number k. Does this graph have a vertex cover of size k? Right, not a minimum one, but one of size k. And here the vertex cover is a subset of the vertices with the property that for every edge, at least one of the two endpoints belong to this subset U of the vertices. So that means that also vertex cover problem is in NP. This is precisely the syntactical form of NP that we've learned about, namely binary encoding of something that's Rx. There exists a witness, so here in order to reformulate whether there exists a subset of the vertices, we've rephrased that as a binary string that serves as characteristic function of this subset. And the length of that binary string is polynomial. So we're good about this condition. And verifying that it is, vertex cover can be done in polynomial time. Just look at all possible pairs of edges or all possible edges, that's polynomial time. So that vertex cover problem is also in NP, but here we don't know whether there also exists a polynomial time algorithm. We've seen, it was easy to see that this is in NP, but whether it's actually in P, that's a hard question. That's a very hard question. That's basically the question worth $1 million. So this is about edge cover and vertex cover, which seem in a sense similar to our previous slide on Eulerian cycle and Hamiltonian cycle. Superficially, the both problems look basically the same, but one of them turned out to admit a polynomial time algorithm, and for the other problem, we don't know. Might or might not admit a polynomial time algorithm, Hamiltonian cycle and vertex cover problem. Now let's consider one other final pair of problems, the Clique problem. Clique problem is the following decision problem. Again, it comes from a maximization problem. In this case, let me find a largest clique in a given graph. We say it again. Given a graph, find the size of a largest clique in this graph. So to remind you, what is a clique? A clique is a complete graph. So here in the right, you see a clique of size 7. This is a graph of 7 vertices, and any 2 vertices are connected. There are lots of edges in a clique. And if there is such a clique of size 7 in a graph, then we might be interested in checking whether it also has a clique of size 8 or 9 or 10, or what is the size of a largest clique in a given graph. So this is an optimization problem, a maximization problem. And again, we can easily reformulate that optimization problem as a decision problem, and thus apply our complexity theory here, namely the decision problem given a graph and given a natural number. Does that graph have a clique of size k, where k is that natural number? That's a yes/no question. Another yes/no question, another decision problem about graphs we're interested in is the independent set problem. Similarly, the independent set, we're looking for a maximal set of vertices that are pairwise not adjacent. So this is the hereditary graph property. If the graph does not have independent set of size k, then it does not have an independent set of size k plus 1 either, but it might have an independent set of size k minus 1. So we're looking for the maximal pairwise independent subset. This is again an optimization problem like the Clique problem. And again, this is a problem that belongs to this class, syntactic class. NP here, witness could, for instance, be the k-tuple of pairwise non-adjacent vertices. And there it is easy to check that these vertices are pairwise non-adjacent, that there's no edge between any two of these vertices. The difficult part is finding such a subset, convincing someone that there is or that there is no such subset. That's the hard part, independent set. So these are two further examples of problems in this syntactic complexity class NP, and I've refrained from proving that this is equivalent to the semantic definition that maybe some of you are already familiar with. So now we have several decision problems, shown them all to belong to this class NP. For some, we've been able to show them actually to just belong to the class P, and for others we have not. But this does not mean that they are not. It just means we haven't been able to prove nor disprove. Which raises the question, why is that so? Can we do something about this? Can we do science, complexity theory about this question without knowing the answer to this question? And the solution to this meta problem of science is, yes, we're able to compare the complexity of decision problems without knowing the complexity of the decision problems. This is, I have said this before, this is a pinnacle of the scientific method, dealing with uncertainty in computational problems. Here the uncertainty refers to whether a given problem can be solved in polynomial time or not. So let's recall the Clique problem and the independent set problem, and let's consider some example graph drawings. So here you see a graph with 9, I'm going to say 9 vertices and many edges. I'm not even sure how many. And my claim is that this graph has an independent set of size 4. Let me say it again, this graph has an independent set of size 4. There exists a subset of the vertices which are pairwise not connected. Anyone see this subset? Anyone able to convince me that this graph has a subset of the edge of the vertices of size 4 that are pairwise not connected? Here's a hint. Look at the red vertices, which for some reason have been colored red, maybe for pedagogical reasons, yes. So let's look at these two red vertices. There's no edge between these two vertices, so these two vertices are not connected, they are not adjacent. That's graph terminology. Now let's look at these two red vertices. Again, there are many edges, but not between these two red vertices. So these two red vertices are not connected. Now let's look at these two red vertices. There are many edges here in this graph, quite distracting, but between these two red vertices, there is no edge. So now we've already found 3 vertices, these 3 red vertices that are between which there are no edges there. Any 2 of these vertices are not connected. There are no edges between these vertices. There are edges from these vertices to other vertices, to the green ones, but not among the red vertices. And the same remains true when we throw in this additional red vertex. Now we've already found 4 red vertices between which there are no edges. So that means in this example graph there exists an independent set, IS, of size k equals 4. And that's the largest we can get. There is no independent set of size 5. If any choice of 5 vertices, there exists at least one edge among these 5 vertices. So that the answer to the optimization problem independent set here is 4. 4 is the largest independent set. Or put differently, as this decision problem, when k is equal to less or equal to 4, then the decision problem here has answer yes. When k is 5 or larger, then the answer is no. Good. So that's one example instance for the decision problem independent set. And let's now look at another example instance for the decision problem Clique. So for Clique, the question is to find a subset of the vertices as large as possible. It's a maximization problem that are pairwise connected. Okay, anyone can find a large subset of vertices that are pairwise connected in this example graph. Again, look at the red ones. The red vertices are pairwise connected, right? Between any two red vertices, there's an edge. The red vertices form a clique of size 4, a 4 clique. And this is the largest clique contained in the graph. So in this example, the answer to the clique maximization problem is 4. In this example, the answer to the clique decision problem is yes when k is less or equal to 4, and no when k is strictly greater than 4. So now we've seen two example instances of these decision problems whose complexity we still don't know. And we've seen some similarity in the example. Maybe in the first example, there was the red vertices would form a large, a maximal independent set, maximal set of vertices that are pairwise not connected. And in the second example, the same, observe that this is the same set of vertices, form a maximal clique, a clique of size 4, and there's no larger clique. So is that coincidence? Let's look carefully at what is the relation between the two graphs examples. I'm going to switch back and forth quickly. What do you observe? You may observe that when there's an edge present here between any two vertices, then between the same two vertices, the edge is absent. And if there's an edge present here between some two vertices, then this edge is absent here. This is called the complement of a graph. So one graph is the edge complement of the other. Whenever an edge is present between two vertices in this graph, then the very same edge is absent here, and vice versa. So that these graphs are mutually complementing each other. And whenever there's an independent set here, after complementing, this independent set has become a clique of the same size. And vice versa, whenever there's a clique here, then this gives rise to an independent set of same size here. So that in a sense, it seems that at least in this example, the two problems are basically the same. They're the opposite of each other, right? Can we somehow formalize this idea that the two decision problems seem to be basically the same? And this formalization is what is called polynomial time reduction. This is the core concept of computational complexity theory. This is the invention, half of what made Stephen Cook famous. If you want to know about the other half, please sign up for the course CS422 next time. So what is this polynomial time reduction? Here's the formal definition. Let's consider two decision problems let's call them K and L, and we want to compare them and be able to speak and to say that K is at most as difficult as L, without knowing the inherent computational complexity. And the notion of a reduction means converting the first decision problem into the second decision problem in such a way that the answer remains the same in both cases, that an answer, a query X, is to be answered positively. X belongs to the decision problem K, if and only if the translated query f of X belongs to the second decision problem. Okay, so the time is up for today. To summarize, we've made big strides into a very brief recap of classical discrete complexity theory. We have learned about the complexity classes P and exponential time, and NP, which means polynomial time verifiability. And we've seen example problems from these classes. So next lecture on Thursday, we're going to continue talking about means of comparing decision problems by means of polynomial time reduction, properties of polynomial time reduction, such as transitivity. And then we're going to more closely discuss two famous problems in NP, the knapsack problem and the traveling salesperson problem, before we then proceed to chapter 8 about approximation algorithms for this knapsack and for this traveling salesperson problem. Thanks everyone for attending. Thanks for being here. I'll stay online as usual for a few more minutes and then let the TAs take over the discussion. Feel free to ask questions about the homework and see you again.